Now let's just move on further towards a very special theorem which is called as the Pythagoras Theorem. But before going towards the proof of the Pythagoras Theorem or the statement of the Pythagoras Theorem, we will discuss a very special important theorem which will help us in the Pythagoras Theorem. So let's just see that theorem. The theorem says that if a perpendicular is drawn from the vertex of right angle of a right triangle to the hypotenuse, then the triangle on both sides of the perpendicular are similar to the whole triangle and to each other as well. So let's just start the proof of this theorem. First of all, we'll start with the given conditions that what are given to us. So as we can see over here, it is given to us that there is a right angle triangle. So let us suppose if I'm starting with a right angle triangle, given a right angled triangle A, B, C. Let us suppose if I'm taking right angled at B. Let us suppose if I'm taking a right angled triangle ABC, which is right angled, that is, it is making a right angle at the B vertex. And further, let us suppose if I'll draw the right angle triangle over here. Okay, so this one is our right angle triangle such that I'm taking a right angled at B. So let us suppose if I'm taking this one as B and this one as A and this as C. Let us suppose if I'm taking it in such a manner. Now again it says if a perpendicular is drawn from the vertex of a right angle of a right triangle to the hypotenuse, then the triangles on both sides of the perpendicular are similar to the whole triangle. So let us suppose if I am just taking a perpendicular which is drawn from the right angle, so it means there is a perpendicular over here. So let us suppose if I am calling it as nothing but D, it is nothing but D. So the given statement is a right angle triangle ABC right angled at B and a perpendicular, that is BD, which is drawn to AC. As you can see over here, BD is drawn to AC. So let us suppose if I'm just writing a construction over here that I have drawn, BD perpendicular to AC. Now what we have to prove? We have to prove that the triangle ABD is similar to the triangle ABC. The triangle BDC, let us suppose, is similar to the triangle ABC, and further we have to prove that the triangle ABD is similar to the triangle CBD. So these are the three things that we wanted to prove, or we have to prove in this particular theorem, that first of all, a very first triangle, this one, is similar to the whole triangle ABC, and this triangle is similar to the whole triangle ABC, and further this triangle is similar to this triangle. Now these are the three things that we have to prove. So let's just start the proof of this particular theorem. First of all, as we can see, we have to prove that ABD, the smaller triangle, is similar to the whole triangle. So let's just start the proof of the very first part. So let's just start with the proof. So the proof for the very first part would be like the proof of the very first part. So as we can see, in the triangle ABD, in the triangle ABD and the triangle ABC. So let us suppose if I am taking the two triangles over here and I am starting with the triangle ABD and triangle ABC. So what are the things that are common in the whole triangle ABC and this triangle ABD? First of all, as you can see, angle A is equal to angle A. It is common to both. Angle A is equal to angle A. It is common to both. And the other thing is that the angle D is equal to the angle B, because each are actually 90 degrees. So as you can see, angle D is 90 degree over here, and further the ABC, in the ABC triangle, B is 90 degree. So it means by angle similarity criteria, these two triangles are actually similar to each other. So it implies triangle ABD is similar to the triangle ABC by angle similarity criteria. So hence the very first part is done, that we have proved that the triangle ABD is actually similar to the triangle ABC. Now let's just talk about the second part. So second part is actually again similar. Let us suppose if we are starting with in the triangle BDC and the triangle ABC. So as you can see, angle C is equal to angle C. They are common in both. Further, as you can see, angle D is equal to angle B. Each are 90 degrees. So hence again we can say that the triangle BDC is similar to the triangle ABC. Why so? Because by the angle similarity criteria, we can say these two triangles are similar to each other. Now let's just talk about the very third part. In the third part, we have to prove that ABD is similar to CBD, means these two triangles are similar to each other. So let's just start proving this part. So as you can see, in the triangle ABD and the triangle CBD, in these two triangles, first of all we know that angle D is actually 90 degree. So we can say angle D, or we can say angle BDA is equal to the angle BDC. Each is 90 degree. So this is my first statement that we have, that each angle over here is 90 degree. Now let's just further talk about the other angles. Let us suppose if I'm taking this angle as nothing but angle 1, I'm taking this one as angle 2, I'm taking this one as angle 3, and I'm taking this one as nothing but angle 4. So what are the things that we can say about the angle 1 and angle 2? So let's just see a relationship. As in this triangle, if this angle is 90 degree, if this angle is 90 degree, so what can we say about angle 1 plus angle 2? We can say angle 1 plus angle 2 is equal to 90 degree. It would be 90 degree. Why so? Because of the angle sum property of a triangle, we know that if this angle is 90 degree, then their sum is also 90 degree. So it implies again this condition is also applicable to the angle 3 and angle 4, because if this angle is 90 degree, then sum of these two angles would be 90, because that's why we'll get the sum of all the angles of this particular triangle as 180. So it means angle 3 plus angle 4 is 90 degree again. And further we can say angle 2 plus angle 3 is nothing but 90 degree. As you can see over here, we know that angle B is 90 degree and this is angle 2, this is angle 3. It means the whole sum is definitely 90 degree. So what can we conclude from these three things? As you can see, if angle 3 plus angle 4 is 90, angle 2 plus angle 4 is 90, if we'll take the comparison of these two, we will get angle 2 is equal to the angle 4. So we will get angle 2 is equal to the angle 4. And furthermore, if I'll compare these two, then we can see over here that angle 3 is actually is equal to the angle 1. Angle 3 is actually is equal to the angle 1. And hence you can see over here, that this angle, that is angle 2, is equal to the angle 4 of this particular triangle, and angle 3 of this triangle is equal to the angle 1 of this triangle. And furthermore, we know that angle BDA is actually is equal to the angle BDC. Hence, by the angle similarity criteria, we can again say that the triangle ABD is similar to the triangle CBD by the angle similarity criteria. By the angle, these all the three angles. So by this angle similarity criteria, these two triangles are similar to each other. So this is all about this theorem, in which we have proved that if a perpendicular is drawn from the vertex of a right angle of a right triangle to the hypotenuse, this is my hypotenuse AC, then the triangles on both the sides of the perpendicular are similar to the whole triangle, and thus they are similar to each other. So this is the theorem that would lead us towards the Pythagoras theorem, because we will definitely use this theorem in the Pythagoras theorem. So let's just see and move on further towards the Pythagoras theorem. Now let's just see the Pythagoras theorem. Pythagoras theorem says that in a right triangle, so if we are talking about the Pythagoras theorem, then we are working in a right triangle. So in a right triangle, the square of the hypotenuse is equal to the sum of the squares of the other two sides. So we have to prove this theorem that in any right triangle, the square of the hypotenuse is equal to the sum of the squares of the other two sides. So let's just start the proof of this theorem by drawing. Let us suppose if I'm drawing a right angle triangle over here. So let us suppose if I am taking a right angle triangle in such a manner, and I'm calling this as nothing but ABC. So this is my A, this is my B, let us suppose, and this is nothing but my C. So let us suppose if I'll write over here that given a right angle triangle ABC, right angled at B. So let us suppose if I am taking it as a right angled at B. So what we have to prove, but before that, let us suppose if I'll write the construction over here which is required. So I am taking a construction over here that I am drawing BD perpendicular to AC. I'm just taking a perpendicular BD over here, which is perpendicular to the AC. Now let's just talk about to prove what we have to prove. We have to prove that the hypotenuse, that is AC's square, is nothing but is equal to AB square plus of BC square. This is the thing that we wanted to prove, that the hypotenuse square is equal to the sum of the squares of the other two sides, and the other two sides are definitely AB and BC. Now let's just talk about the proof of this theorem. So let's just start with the proof of this theorem. So as you can see over here, if we have this particular triangle, then by the previous theorem we know that if any perpendicular is drawn from the right angle of a right angled triangle towards the hypotenuse, then this particular triangle would be similar to this triangle, and each triangle is similar to the whole triangle. So from that particular theorem we know that if I'm talking about the triangle ABD, then this is definitely similar to the triangle ABC whole. So we can say that the triangle ADB is actually similar to the triangle ABC. So I am writing it over here by the previous theorem that we have done already, because I told you that we will use that theorem in the proof of the Pythagoras theorem. So I'm just writing it over here by the previous theorem. By the previous theorem we can say this fact that whenever we will draw a perpendicular from the right angle of a right angled triangle towards the hypotenuse, then this triangle would be similar to the whole triangle, and each are similar to each other again. So if this particular triangle is similar to the whole triangle, then what can we say about the ratio of their corresponding sides? So the ratio of their corresponding sides should be equal to each other. So it means that I can write it over here that AB, let us suppose if I'm starting with AB or AD, let us suppose we can take any particular side. So let us suppose I'm starting with AD. So we can say that AD by AB is actually nothing but is equal to AB by AC. We can say this thing. Why so? Because since sides would be equal, since as we can say, since the triangles are similar. So since the triangles are similar to each other, so we can say this fact that the corresponding sides ratio would be equal to each other. So let us suppose if I'll solve these ratios, so I can see over here, if I'll solve them, so I can get a relationship as nothing but, let us suppose if I'm starting from here, so we can write it over here that AD into AC is actually nothing but is equal to AB into AB, and furthermore I can write it as nothing but AB whole square is equal to AD into AC. So let us suppose if I'm taking it under a box and I'm calling it as nothing but my equation number 1. Now let's just move on further and we can talk about the triangle BDC and the whole triangle ABC. Now again, Similarly, I'm just talking about the two triangles again. The triangle BDC is similar to the triangle ABC. Again, why so? By the previous theorem we can say about this fact. by the previous theorem, we can say about this fact that these two triangles are actually similar to each other. So if these two triangles are similar to each other, then again their corresponding sides ratio would be equal to each other. So hence it implies that BC by CD, we can say BC by CD should be is equal to, or we can say CD by BC. We can take it in such a manner as well, that CD by BC should be is equal to BC by of AC. So let us suppose if I am taking it in a reciprocal manner, I am taking BC by CD should be mandatorily equal to, it should be is equal to, as you can see over here, it should be is equal to AC divided by BC, AD divided by BC. So this is again because of the reason that the two triangles are similar, so their corresponding sides ratio would be equal. So we can say since the triangles are similar, so we can write this particular fact. Now let us suppose if I am solving it out, so this would be BC into BC, which is nothing but is equal to AC into CD. Now again we can write it as BC square is equal to AC into CD. Let us suppose if I am calling it as nothing but the equation number 2. Now let's just add up the equation number 1 and 2. So let us suppose if I am add 1 and 2, so this would be nothing but AB square plus BC square is equal to AD into AC plus of AC into CD. So there is something that we can take out common in this particular expression. As you can see, we have AC common. So let us suppose if I am taking AC common, so this would be AD plus of CD. So as you can see, AD plus of CD is nothing but actually the whole AC. So this would be AC into AC, and hence this is nothing but AC square. So at the end what we are getting AB square plus BC square is equal to AC square, and this is exactly the thing that we wanted to prove. So hence proved the theorem that the square of the hypotenuse is nothing but is equal to the sum of the squares of the other two sides in a right triangle, and this is nothing but called as the Pythagoras theorem. So there is a very important fact that this theorem was also stated by a great mathematician Bodhian in a different manner. So that's why it is also called as the Bodhian theorem. It is also called as the Bodhian theorem. Pythagoras theorem is also called as the Bodhian theorem because it is also stated by the great mathematician Bodhian. So this is all about the Pythagoras theorem. Always remember, in a right triangle, the square of the hypotenuse is equal to the sum of the squares of the other two sides.